Welcome back. Today we will be continuing our previous topic from the solid rocket propellant motors, and myself, I am Sai Krishna from the Department of Aeronautical Engineering. We will be studying the aerospace propulsion. Right? In the previous class, what we have discussed basically the thermodynamic characteristic and the thermal part, right? Particularly the heat that is being integrated for the nozzles of a solid rocket propellant motor. Now, in this session, we will be discussing regarding the ignition, right? In what way the ignition in a solid rocket motor works, as well as a few factors that are important to sustain the same ignition or the flame, right? The solid rocket motors are used in particular two applications. First, both which require ignition as well as should be stable as well as reliable for a liquid fuel engine. The main propulsion unit for the rocket stage or satellite orbital injection systems requires timely ignition in order to achieve the eventual orbit. A booster forms one of the group of motors which must be developed just together. In all cases, a pyrotechnic igniter is used. Right? We'll understand this. Right? What do you mean by pyro? Is nothing but study of combustion, right? Or study of combustion fuel, and technique means methods. Now, pyrotechnic devices are the devices which have an extensive as well as reliable heritage, particularly for the space use and in variety of different applications. To ignite a solid rocket motor, a significant charge of pyrotechnic material, particularly a small explosive material, is needed to ensure that the entire inner surface of the surface grain is simultaneously brought to the ignition temperature, right? For example, this is my case and this is my propellant charge. Right? Now, what happens in this case? Basically, whenever we want to ignite our solid rocket propellant booster, particularly complete set, what will be happening? This will be my completely exposed surface. Right? This will be my completely exposed surface which is ready to burn. Right? Now, in order to burn this, we are supposed to ignite. Simple to as a wick inside an oil lamp, right? A wick inside an oil lamp. What we are supposed to do in order to have some flame, we will be igniting it initially through an external source, right? The same external source in our case is nothing but my pyrotechnic device. Now, what does a pyrotechnic device have? Is basically a charge of explosive material or a small packet of explosive material which is such efficient, or as it burns, right? It has the capability to start the ignition, right? Start the self-ignition of the entire surface, entire exposed surface to start burning, right? To start burning. Now, as soon as it starts to burn, it tends to move further, right? As soon as it starts to burn, that as it burns on, right? Initially, as the surface burns, as we know, as the upper layer gets converted and burned into your combustible gas or exhaust gases, the lower layer tends to evaporate furthermore and converts itself into gaseous form, then you burn again, right? Now it's a continuous process, right? But initial start, right? Let's say whenever you want to start solid rocket booster, what you'll be doing, you will be starting, particularly you will be igniting with a pyrotechnic material in such a way that complete inner surface of the grain is simultaneously increased, particularly brought up till the ignition temperature of propellant. or in our case charge or crane, right? Now, continuing the same, solid propellant ignition, which comprises of a series of complicated as well as a rapid event that are required to start upon the recipient of signal, particularly an electric signal, that ignites the propellant and has the hot gas flows from the igniter to the motor grain surface. Spreading of a flame over the entire burning surface area, particularly filling the chamber cavity with gases and elevating the chamber pressure without serious abnormalities such as overpressures, combustion oscillations, or damaged shock waves or hang fires, which means a delayed ignition, flame extinguishment, or chuffing. Right? We'll undergo this. Now, when we want to start a solid rocket motor booster, right? What we're having basically, as we discussed earlier, the propellant charge, a case, right? The same thing is followed on the opposite side if I consider for cylindrical hollow type of charge. Now, at the end of the casing, right, we'll be having small pyrotechnic charge, nothing but a small explosive packet. Now, when we want to start my solid rocket motor, this pyrotechnic charge will get signaled, right? Signaled by electricity, because electricity travels at much faster rate than any other signal, right? So as soon as it gets the signal of electric signal to start the engine. What it basically does is the pyrotechnic device explodes itself, right? As it explodes, it creates the initial charge burn plus temperature pressure, right? What happens now as the charge burns? What happens? The initial area gets burned, right? Fastly converting my propellant material or grain material directly to gaseous form, then creating my required temperature as well as pressure, particularly pressure. Now, based on the pressure, the grain surface or the grain which is the surface which has been exposed, right? Exposed to my charge or the cavity. What happens during this? They tend to burn faster, right? They tend to burn faster, giving out more amount of gases, particularly gases. Now, as the gases are being expelled out, they will be sent through my nozzle, creating the required thrust. Basic as such. Now, during this, what are the abnormalities that we can find or we usually occur is basically the overpressures, right? What do you mean by overpressures? Basically, the nozzle has been designed to withstand certain pressure, let's say some 10 bar, but the pressure generated by my initial charge, particularly the pyrotechnic charge, as well as the grain will exceed this 10 bar, creating a small pressure abnormality at the nozzle, right? Other one would be my combustion oscillation, right? The combustion is not uniform, right? For example, larger amount of gas is being formed at one side of my charge rather than the other side, right? Now this gives me what? A higher rate of erosion or higher rate of burning from one side rather than the other. Now this gives an unequal distribution of the propellant of the whole charge or the whole rocket motor, as well as it gives me a oscillation, right? It will be a periodic form. Sometimes there will lows and this will be mass. It oscillates. Next one will be damaging shock waves. The waves, particularly the exhaust pressure what it has, as it gets out, the shock waves that are being produced inside the cavity due to the burning, what happens? These shock waves might be damaging in nature. It might damage the charge or it might damage the case in which it is being fit. Now these shock waves tend to move further towards the nozzle, giving me the damage to the nozzle itself. Next one will be hang fires, which means delayed ignition. What I mean by that is basically whenever we tend to start the ignition of solid rocket motor at, let's say, 5 seconds or at 0th second, right? And now as soon as my signal give, within a fraction of millisecond, it's supposed to ignite my solid rocket motor. But let's say for hang fires, they tend to delay much slower, right? They tend to delay. For example, same thing. The propellant charge, whatever we are having, is burning very slowly, right? Particularly the surface near the explosive part tends to burn faster rather than everything else. This created my delayed ignition. Other one would be the flame extinguishment. If there is no sufficient pressure, temperature, as well as the propellant available, the flame, particularly the ignition flame, tends to extinguish itself, right? So in order to minimize that, what we are supposed to do, we are supposed to maintain proper proportions of the propellant as well as the gases, particularly temperature and pressure, to sustain, right? To sustain the flame, right? The igniter in a solid rocket motor is the component that heats and generates the gases that are necessary for the rocket motor ignition. The rocket motor ignition must usually be completed within fraction of seconds, but for very large motors. The pressure inside the rocket motor rises to its equilibrium state in a very short time, as shown in figure. Right? Let's consider this as a figure. Typical ignition. Right? Typical ignition pressures are plotted in this, where the dotted curve, which shows the igniter pressure for particularly any pyrogen type, particularly any nitrocellulose or any explosive. Now coming to this darker line is for other, right? Now what happens under this time, which is represented in milliseconds, which is again displayed or plotted against the igniter pressure as well as the chamber pressure. Now what happens under this first phase, ignition phase, within the short duration of time, particularly the phase 1, within the shorter duration of time, what happens? There will be no motor pressure, chamber pressure inside the rocket motor, but we will be having, as soon as the signal gets initiated, let's say I am giving a signal out to start my engine. At the time, the pyrotechnics, particularly the igniter pressure, will rise rapidly, right, to a point where it will explode itself to creating the required environment for starting of my motor, right? Now as soon as it's getting exploded, I mean all the work is done, the pressure tends to move or reduce over a period of time. Now what happens during this period? Basically, as the explosion is taking place within the phase 1, there might be a small amount of pressure that is being generated, but it's not sufficiently enough to maintain that pressure. So during this, what happens? As the complete ignition process is done, particularly the igniter process work is done, what happens? This tends to increase gradually, which gives us the region between phase 2. What happens under phase 2 is basically there will be an increasing motor chamber pressure, but gradual or a nominal decrease in my igniter pressure. But whereas for phase 3, the water chamber pressure will attain its equilibrium, right? It means, so based on my grain design, particularly the grain shape or structure, the attain the pressure inside a motor chamber pressure will tend to attain its equilibrium, means there will be minimal pressure differential between two subsequent seconds or two subsequent time frame. Now coming to your igniter type, as the pressure that is being generated is completely dependent on the solid rocket motor charge, these tends to drop further, such that after a certain period there will be no pressure relative to my igniter, right? That will be directly comes to zero, whereas the pressure will be dependent on my grain. So what does the figure say? The electric signal is received a few milliseconds before the time zero. Before the time zero. So as the time, let's say, for in a rocket launch, if this is my 0th second and there is a countdown going on till 0, before few seconds, particularly milliseconds before 0, you will be giving out the signal. Now based on this signal sent to my pyrotechnics igniter, they tend to start the engine from 0. So my during phase 1 the igniter pressure is higher, later again it will decrease, right? During that period, let's say for 1 second or 5 seconds, my actual motor's drain will tend to give out my required performance, right? Conventionally, ignition process is divided under 3 phases for analytical purposes. That is the phase 1, that is the ignition time lag. What do you mean by this ignition time lag? Is the period from the instant that the igniter receives the signal, that is the electric signal, until a portion of the grain surface is burned to produce the hot gases, right? What we had discussed earlier is the same. As the igniter gets burned or starts, you will be initially burning a small portion of my grain, right? As this burns, you will be getting my initial amount of hot gases as well as the surface burn, starting off my surface burn. Now coming to phase 2, which is the flame spreading interval, and it is a time from the first interval of the grain surface until complete grain burning area has been ignited, right? First the surface area, next one will be the chamber filling interval, the time for completion of chamber gas filling process and for reaching equilibrium chamber pressure and mass flow, right? As soon as the flame gets spread onto my surface, what is the time or what is the duration that is being taken by the grain to maintain the burn as well as to build up my pressure and required mass flow rate for my nozzle, because actual flow of my mass flow rate as well as the pressure gives me my final momentum, final velocity from the solid rocket motor. Now, ignition will be successful once sufficient grain surface is ignited as well as burned, so that the rocket motor will maintain to continue its own pressure up to the operating chamber pressure. If the igniter is not powerful enough, some grains may burn only for a short time and the flames will be extinguished. The relevant critical processes seem to be located in gas phase reaction above the surface reaction, where the propellant vapors and or decomposition products interact with each other and with the igniter gas products. Now, what happens under this case? As we are starting, as due to, let's say, for due to my igniter, the corner of my surface gets burnt. As soon as the top of the corner gets burnt, the upper surface, which is exposed to the cavity that is being having inside, will get burnt, right? Now, as soon as it gets burnt, what happens? They tend to increase temperature, pressure majorly. Now, what happens during temperature and pressure? Now, a gas phase reaction, right? Whatever we are having propellant, that is in solid phase. Why the gas phase? Because the solid phase of the propellant will get evaporated, right? Evaporated due to the temperature and pressure that is being generated inside the casing to convert itself into solid to gaseous phase, particularly by burning. Now, as it burns, it tends to move further, creating the required pressure or the optimum burning temperature, and where the propellant vapors, particularly the unburned vapors, as well as the decomposition products, particularly using aluminum or any other additive materials, they tend to interact each other with igniter gas products, right? From the igniter gas products, creating our abnormalities that we have discussed earlier, right? For satisfactory attainment of an equilibrium chamber pressures with full gas flows, which depends on first the characteristic of igniters as well as the gas temperature, composition, and issuing flow. What kind of igniter we are using, and what is the resulting gas temperature, what is the composition of the gas, and how well it will be maintaining the flow that is required by us. Next one will be the motor propellant composition as well as the grain surface ignitability. What is the composition of my solid rocket motor, right? That we are supposed to understand clearly or while before manufacturing. And what are the grain surface ignitability means? The ability of the grain, particularly the propellant, to ignite, right? It means at what temperature the grain tends to ignite itself on its own. That temperature we are supposed to maintain or create based on the type of igniter we choose. If you are choosing a wrong igniter, we will not be able to create that required temperature, so that the propellant might not be able to burn. Next one will be the radiation as well as the convection heat transfer that takes between the igniter gas as well as the grain surface. That also we are supposed to maintain or look after. The grain flame spreading rate. For example, any dry grass, if I find an example for dry grass, what happens as soon as we ignite, right? As soon as we ignite one part of the dry grass, it tends to spread faster to other areas that are surrounding it. What happens if for a green grass? It tends to move not much further. Next, the dynamics of filling the motor free volume with hot gas. With what speed, right? With what speed inside the cavity we tend to fill with the gases that are being generated from my exhaust gases, particularly the igniter gases. Next, the quantity and the caloric energy that are needed to ignite a particular motor grain in its prevailing environment, means the ambient environment, which has a direct bearing on most of the igniter design parameters, particularly those affecting its required heat output. Propellant ignitability is affected by several factors, particularly propellant formulation, what kind of propellant we are using, what are the additives, what are the binders we are using, what is the combination of them which tend to burn faster. These are all we will be looking after. Next, propellant grain surface initial temperature. If the propellant grain is under low temperature, what happens? They tend to, in order to convert it to gaseous form, we need to put up for more temperature from the igniter side, right? If the propellant surface is at somewhat moderate temperature, what happens? The igniter power can be somewhat less compared to previous. If the temperature is somewhat high, the igniter small charge of explosive might do the work. Next will be the surrounding pressure, the pressure at which the grain is being embedded, as well as for the pressure that is being generated from the igniter gases, right? These two will depend or which include itself as the propellant ignitability factors. For example, if majority of the solid rocket motor boosters are used for as boosters in atmosphere, particularly during initial launch stages, lower stages. What happens during that? The pressure will be equivalent to the atmosphere, but only thing that changes is the igniter pressure, right? The based on what type of igniter we use, the pressure inside the chamber changes. Next one will be the modes of heat transfer, right? What are the types of heat transfer, particularly what particular radiation, convection, conduction, right? Making use of either one or a combination of these type of modes, what is the best possible way to transfer the heat, right? To transfer the heat among the propellant, particularly the igniter gas, to burn surface or the exhaust gases or charge, right? In what way the heat interaction will be taking place among all these, right? Based on this, we are supposed to convey or create the best possible propellant formulation to ignite the same. Next one will be my grain surface roughness. What is the roughness that it can take, right? As we know, the finer the grain size, the better the combustion, but not in all cases. Sometimes the bigger the grain size is used to bind the particle, bind the charge together. Next one will be the propellant age. If it's a newly built propellant, particularly a newly formulated or newly molded propellant, it tends to burn faster compared to somewhat old, because as being fresh, it tends to have much faster rate of burning. Next one will be my composition, particularly the hot solid particle content of the igniter gases. In our case, it will be, let's say for example, aluminium. We will be using aluminium to increase the particular sections, particularly ignitability of the gases. Next one will be igniter propellant and its initial temperature. What kind of propellant we are using for ignition, particularly the pyrotechnic charge, and what is its initial temperature. If it's lower temperature, upon burning they might lose some temperature, whereas for others it is better. Next one will be the velocity of hot igniter gases relative to the grain surface. What is the velocity at which these gases move in respect to my grain surface inside the cavity. Next one will be the what is the cavity volume that is available. As we have discussed earlier, cylindrical, cork shaped, gear shaped, concentric one. All these are dependent to maintain my cavity, right? This gives us the area through which the exhaust gases are supposed to propel as well as maintain the required pressure inside the chamber, right? Now with this we will stop it, and furthermore we will be discussing regarding the igniter types, and next one will be our solid rocket propellant examples. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.